Hi, my name is Mitali Gupte and this is Lab 1 for Physics 2211. This lab observes a real-world object at constant velocity to demonstrate the implications of Newton's second law. In particular, a golf ball was rolled at a constant speed on a flat table. A camera and tracking software were used to record observations and create a computational model. Computational models help us translate observations into predictions and are an important tool in physics. By comparing our computational and observational models, we can better understand the nature of Newton's second law when predicting the motion of objects. I observed a golf ball moving across a flat surface. I was able to analyze its motion and calculate position and velocity values using the tracker software. This information was used to build my computational model. I collected data from the ball, such as mass and diameter. I also recorded the start and end times of the system. The initial position of the ball was recorded using the tracker software. In order to calculate the average velocity, I followed the formula shown at the top right-hand corner. I took the second evaluation point at time 2.867 seconds and subtracted it from the initial position at time 0 seconds. The average velocity is shown in the vector at the bottom, negative 9.689 e negative 1, 0, 0. I used the GlowScript code to model my system. Mass, position, and average velocity vectors were used for data. The net force vector was set to 0, 0, 0 in order to model constant velocity. The velocity and position formula were updated to reflect the average velocity as well. This is a model comparison of the tracker and GlowScript graphs. Tracker reflects the observation that I made, and GlowScript reflects the computational model in a perfect system. By compiling the data from these two models, I was able to show them in one graph. While the lines are not aligned perfectly, they are considerably close to each other. The model data is in a straight line because it represents a perfect system in which no outside forces affect the constant velocity. The observed data indicates that other forces were acting on the ball, causing it to slightly accelerate then slow down. What if we flip the axis of orientation? Originally, my object moved in the negative x direction. If I chose to reorient my object in the positive x direction, its direction vector would change, while its relationship to the axis would not change as long as the object's velocity remains constant. Considering the change in direction, a graph of the object's time versus position will look approximately as pictured, with the arrow facing up towards the right. Is it possible to say how many pushes and pulls are added together to give a zero net force in the case that I observed? While I can name a few forces that were acting on the object, such as my hand, the friction on the table, the upwards force of the table, and gravity, I cannot say exactly how many forces it would take to create a zero net force. This is because there are a lot of smaller forces at play, as shown by the difference between the modeled and observational graphs. This lab demonstrated how an object can move at a constant velocity when applied with a net force of 0 due to momentum. It explains how objects have the ability to keep moving after an initial force is applied. The lab also allowed us to use computational modeling to better understand the nuances of natural observation in an imperfect system. It demonstrated how there are a variety of smaller forces in the real world that act upon our systems. Due to these smaller interactions, it is beneficial to look at both observed and modeled data sets when exploring principles such as Newton's second law. Thank you.